August 17th, 194,327,000 feet above Schweinfurt, Germany, inside the nose of a B-17 flak. Lieutenant James Howard hunches over America's most classified of equipment, more secret than another, more protected than the Atomicum project that won't even start for another 2 years. The Norden Mark XV bombsight, 50 pounds of precision machined, gears, gyroscopes, and glass, worth $8,800. More than 4 brand new automobiles. The device that newspaper headline Esklim can drop a bomb into a pickle-barrel from 4 miles up. Howard's hands are shaking, not from fear, from cold. It's 67 below zero outside the aircraft's plexiglass nose. Through his bombsight's telescopic eyepiece, he can see the target, the Kugeli-Scherbel beer plant, one of 3 factories producing 43% of Nazi Germany's precision bearings. Without bearings, tanks can't move. Aircraft can fly. The entire German war machine grins to a halt. This mission will stop Third Reich. That's what intelligence promised. The formation releases 4,000 pounds of high explosive drop from 183. B-17 segundos. Howard watches through his scope as the bombs fall toward the factory. 36 B-7 South don't make it home. That's 360 men dead, wounded, or captured. The highest loss rate the 8th Air Force has ever seen. In the factory operational again in 3 weeks. According to post-mission analysis, only 88 bombs out of roughly 1,500 dropped hit within the factory grounds. That's a 5.8% accuracy rate with the most advanced bomb sight ever created. But one innovation would change everything. Not because it worked as advertised, but because it changed how America fought the air war. This is the history of the Norden bombsight, the most expensive lie of World War II and the accidental revolution it created. Let's talk about why dropping bombs from airplanes is so brutally implied. You're 5 meters above the earth in AB-7. You're moving at 182 miles per hour. The bomb bay opens. You release a 500 pounds ANM-64 Generalibus bomb. What happens next involves physics that would make your high school math teacher weep. The bomb descent falls straight down. It inherits your aircraft's forward velocity, 182. Note, so, it's traveling horizontally at 182 miles per hour, while gravity accelerates it downward at 32 feet squared. Meanwhile, air resistance slows its forward motion while gravity keeps accelerating it downward. But here's where it gets truly insane. Wind. At 25,000 feet, wind speeds can hit 120 miles per hour. That wind pushes your bomb sideways as it falls, and the wind isn't consistent. It changes speed and direction at different altitudes. A 500 pounds bomb takes approximately 47 seconds to fall from 25,000 feet. In those 47 seconds, your bomb travels through multiple wind layers, each pushing it in different directions. Before, the Norden bombarders used the Mark III bomb. According to U.S. Army aerotechnical manuals, this device was essentially a telescope mounted to an inclinometer, a protractor that measured. The bombardier would estimate wind speed by looking at smoke or clouds. Then he'd calculate in his head, wearing oxygen masks and heavy gloves, in sub-zero temperatures, when to release its bombs. The results were catastrophic. In 1921, General Billy Mitchell's famous demonstration of air power against the German battleship of Fraserland required 65 bombs to sink a stationary. The ship wasn't moving. No one was shooting back. Perfect weather conditions. And it still took 65 tries. By 1940, U.S. Army aero bombing accuracy averaged 1 to 100 feet circular error, probable from 15,000 feet. That means half your bombs landed within a 4-mile set clear around your target. The other half scattered across the countryside. Henadel Ida Eek, later commander of the 8th Air Force, wrote in a 1942 memo, "Current bombsight technology cannot distinguish between a factory and the residential neighborhood. Next to it, from operational altitude, the physics problem breaks down like F. To hit a target, you need to solve for 6 variables simultaneously. Ground speed, your velocity relative to Earth below altitude can stand a shang as pilots climb or descend to avoid flak airspeed. Velocity truth, air mass itself. Wind velocity, 3-dimensional, changing with altitude. Bomb ballistics, drag coefficient, and terminal velocity of the specific ordnance trail angle. The angle between your aircraft's nose and the actual bomb impact point. A human being cannot calculate this fast enough with slide rules and paper tables. By the time you finish the math, you've flown past your target. Think of it like trying to hit a moving target while riding a motorcycle blindfolded in a hurricane, while people shoot at you. That's strategic bombing in 1940. The problem demanded a machine, an analog computer that could solve ballistics equations faster than any human brain. Someone had to build it. Someone did. Carl Lucas Norden, born 1880, Pulgadas, Java, Dutch East Indies, educated in Switzerland, immigrated to America in 1904. By 1911, he's working for Sparigyroscope Company, Designista Bizioncha Systems. For ships, here's what you need to know about him. He was a perfectionist to the point of obsession. He believed machines could do anything humans could do, but better. And he thought precision bombing could make war so terrible that nations would stop fighting. The irony is stickinado, cut with a knife. In 1921, the U.S. Navy contracts Norden to solve the bombing problem. They want to sink enemy battleships from the air. Norden spends the next decade building what becomes Mark XV bombsight, later designated M-Series for Army Air Forces use. Let me walk you through how this works, because it's genuinely the gyroscope core. The left side of the Norden bombsight houses a gyroscope assembly. This isn't like the gyroscope toy you played with as a kid. This is a precision machined rotor spinning at 8,000 RPM suspended in axes. Gimbal system, according to Norden's original patent documents filed in 1931. The gyroscope intends absolute spatial reference. When your B-7 banks pitches or yaws, the aircraft moves around the gyroscope, but the gyroscope itself stays locked on its original orientation. This gives the bombsight a stable reference platform that ignores the aircraft's movements. Think of it like a chicken's head. You've seen videos of chickens keeping their heads perfectly still while their bodies move. The Norden gyroscope does that for the entire optical and computing system. The analog computer, the right side contains computational core. 2,000 precision parts working together as a mechanical Here's how it solves the bombing equation. The bombardier inputs data through calibrated knobs. Altitude knob connected to the aircraft. Altimeter consciousness updates during the bomb run. Airspeed knob set based on indicator sped trail arm. A mechanical linky gethit. The bombarder adjusts to compensate for wind. These inputs feed into a system of gears, cams, and differential missions. According to the Norden Company's technical manual from 1943, the mechanical computer uses gear trains for multiplication and division, mechanisms for nonlinear functions, differential assemblies for addition and subtraction, rate integrators for calculating velocity and acceleration. The computer continuously calculates the bomb's trajectory, solving differential equations mechanically. Every time you adjust the wind correction, gears, mesh, and cams rotate, updating the solution. The output drives the telescope. The bombarder looks through an eyepiece, showing a magnified view of the crosshairs float in the center. As the aircraft approaches the target, the bombardier keeps those crosshairs centered on the target by adjusting turret knobs. Here's the genius part. Those adjustments aren't just pointing telescope. They're teaching the computer about wind, drift, and ground speed. You're programming the analog computer by pointing at the target. The Automatic Flight Control Equipment, AFCE. In 1932, Norden developed the stabilis bombing approach equipment. latter integrated with the Sperry C-1 autopilot. This system links the bomb site directly to the aircraft's flight controls. During the bomb run, typically the last 2 to 3 minutes before release, the bombardier engages the AFCE, that according to the B-7 pilot's manual, control of the aircraft transfers from the pilot to the bombardier's bomb site. The bomb site commands the autopilot, turn to left, increase airspeed 3,000 knots, hold. The aircraft lies itself, making micro-adjustments to keep the crosshairs centered on target. The pilot sits there, hands hovering near the controls, while a box of gears flies his airplane. When the mechanical computer calculates the bomb release point has arrived, when all 6 variables align perfectly, an electrical signal fires the bomb release mechanism. The bombardier doesn't pull a lever. The machine décide. Challenges. The technical obstacles were staggering. According to Navy records from the Naval Surface Warfare Center, early prototypes suffered from gyroscope drift. The spinning rotor would gradually shift orientation over time. Temperature sensitivity. At 60 below zero, lubricants froze and metal contracted, throwing off calibrations bearing wear. The 2,000 moving parts were down during extended missions, introducing error electric radio transmitters and engine. Magnetos created electromagneticos that disrupted the electrocaltrigene system. Norden's team solved this through obsessive engineering. They used exotic metals, beryllium copper alloys for springs, jewel bearings, like those in Swiss watches for pivot points. They designed heat entanglements to keep critical components above freezing. By 1935, the Mark XV passed Navy acceptance trials. Testing results at the Naval Proving Ground in Dogren, Virginia. Bombarders achieved stunning accuracy. According to official Navy reports, the specified accuracy was 2.5 milliseconds, meaning 2.5 feet of error for every 1,000 feet of altitude at 20,000 feet. That's a 50-feet circle. The Navy demonstrated 75 feet accuracy repeatedly. In 1937 tests, the Army took notice. They ordered 80 units in 1938, then 1,000 more in 1939. By 1940, the Norden was America's standard bomb site. Production contracts totaled millions of dollars. The security classification went beyond top. According to Defense Department records, bombarders signed oaths promising to defend the bomb site with their lives. Armed guards escorted every Norden bomb site from factory to. Before each mission, bombarders carried the site to the aircraft in a locked canvas bag. After landing, they removed it and returned it to a vault. If the aircraft was hit and going down, bombarders had to manifesto destroy the Norden with a thermite incendiary charge or physically smash it with an axe. The newspapers called it America's superweapon, the device that would win the war without killing. Precision bombing from 20,000 feet, hitting factories while leaving neighborhoods untouched. Combat would tell a different story. January 27, 1943. The 8th Air Force conducts its first bombing raid on Germany, attacking Wilhelmshaven submarine yards. 53 B-7s equipped with Norden bomb sites reach target. Weather is clear. No cloud cover, light fighter opposition. Nearly ideal conditions. Post-strike. Reconnaissance. Photographs reveal the results. According to the ETH Air Force mission report, approximately 30% of bombs fell within 1,000 feet of the aiming point. That's 3 football fields. The submarine yards remain. This pattern repeats across 1943. Mission after mission, the Norden bombsight fails to achieve anything close to its demonstrated PC. The combat reality. Let's return to Schweinfurt, August 17th, 1943. The first raid, October 14th, 1943. The second raid, nicknamed Black Thursday. The second, Schweinfurt mission sends 291B. 7 Sau. Deep into Germany, they carry Norden bomb sights that cost more than the aircraft carrying them. Theatergat, ball bearing factories producing 22% of Germany's industrial bearings. Kuglischer plant 20% from Veronichto. Kugellager. Ball breaking for the raid costs America 60 B-7 shot down, another 17 damaged beyond. Total 77 bombers destroyed. Out of 2,900 aircrew, 650 are killed, wounded, or captured. According to the Strategic Bombing Survey, conducted after the war, bomb damage assessment reveals 229 aircraft dropped bombs on target, approximately 500 bombs hit inside the factory complexes. That's rally 21.8%. 8% accuracy from Norden-equipped bombers under ideal visibility with clear targeting. Ball-bearing production stops for 6 weeks, then resumes at 70% capacity. By January 1944, production exceeds pre-raid levels as disperse manufacturing Tesmalar facilities across occupied territory. Why? The Norden failed in combat? The post-war analysis identified 5 critical failure modes. 1. Weather. According to 8th Air Force operational analysis, 60% of scheduled missions faced cloud cover over the target. With 810 cloud cover, bombing accuracy dropped catastrophically. The U.S. Strategic Bombing Survey data shows clear weather, 30% of bombs within 1,000 feet. Partial cloud cover 5,710, 22%. Within 1,000 feet. Heavy cloud cover, 810,105% within 1 mile. The Northern Steleskit site was useless if you couldn't see the target. 2. Can be a German fighters attacked bomber formations, starting 200 meters from target. The bombardier station the aircraft knows was the most exposed position. 20 mm cannon fire came straight at U-throw plexiglass. Bombarders reported losing sight of the target during evasive maneuvers. When your pilot is banking 30 to avoid a head-on fighter pass, your gyro stabilized bomb sight maintains orientation, but you've lost visual reference. You have to reacquire a target, reset your drift calculations, and restart your bomb. Often impossible with fighters making repeated attacks. 3. Flak. Herman 88 mm. Anti-aircraft guns created flak boxers. According to Luftwaffe records, Schweinfurt's air defense clad 28 heavy flak batteries, 112 individual guns. Flak forced aircraft to take evasive action during bomb runs. The Nordanarak wired a steady, level bomb run, 4 to 3 minutes. German gunners only needed 30 seconds to calculate firing solutions on steady targets. Pilots faced an impossible choice. Maintain steady flight for Norden accuracy, or take evasive action to serve. 4. Manufacturing tolerance. As Norden production ramped from Dosan's 2000s, quality according to NSWC Dogren records. By late 1944, up to 75% of some production batches failed to meet original specifications. The bomb sights worked, but they weren't accurate. 2.5 ms anymore. They were accurate to 14 milliseconds. More than 5 times worse, and that was just instrumental before adding human factors. 5. Altitude inflation. To avoid flak, bombers flew higher. By 1944, typical bombing altitude increased from 20,000 to 27,000 feet. Every additional 0 feet pounds. The era, wind velocity increases. With altitude, the bomb's flight time increases. Small errors in wind calculation produce huge missed distances at impact. The enemy's German intelligence obtained complete Norden blueprints in 1937. Hermann Lang, a German immigrant working at the Karl L. Norden in Care Factory in New York, photographed, designed documents and smuggled them to Germany according to captured German technical reports. Luftwaffe Ingenieurmann thoroughly their assessment. The device represents competent engineering, but offers no significant technical advantage over bomb sights such as the Lothar Rohr 7. The Germans chose not to copy the Norden. Their aerial doctrine emphasized tactical bombing in support of ground forces, not strategic height. They didn't need the Norden's capabilities. When German Engineersammand crashed B-17s containing intact Norden bomb sights, they confirmed their poor assessment. Impressive, but not revolutionary. What actually worked? The breakthrough came not from the Norden, but from tactics. In February 1944, the 8th Air Force launched Big Week, a series of coordinated raids with long-range P-51 Mustang fighter escorts. For the first time, American fighters could accompany bombers all the way to targets deep in Germany. With fighter escort, bomber formations maintained tighter discipline. Bombarders had steadier platforms. Accuracy improved, not because the Norden got better, but because pilots could fly steady bomb runs without German fighters attacking. According to ETH Air Force records, bombing accuracy improved from 20% within 1,000 feet in 1943 to 50% by war's end in 1945. The Norden contributed, but escort fighters, improved tactics, and overwhelming numbers won the air war, not precision technology. The unexpected advantage. Here's the strangest twist. The Norden's real value wasn't accuracy. It was propaganda. American public opinion demanded Russian bombing. Newspapers published photos of bomb sites and articles about pickle-barrel accuracy. The American people believed their bombers were surgical instruments, minimizing civilian casualties. This political cover allowed the strategic bombing campaign to continue, despite massive casualties and questionable. If the public knew bombers were hitting residential areas often as factories, support might have collapsed. The Norden was a permission slip. We have precision, therefore, our bombing is precise, even when it wasn't. By war's end, Norden and its subcontractor spewed 90,000 bomb sites. Total program costs $1.1 billion in 1940s. Approximately $17 billion. Today, for context, the Manhattan Project cost $2 billion in 1940s dollars. The Norden program cost half as much as developing Gaelic weapons. Post-war service. The Norden remained in U.S. military service until the 1960s. B-52 Stratofortress bombers used modified Norden bomb sights during Vietnam. According to Air Force records, Norden's dropped sensor packages along Ho Chi Minh Trail with finally achieving in peacetime what combat conditions prevented during World War II. The technology, the Norton's real innovation was the device itself. It was proving that automated fire control systems could work. Modern precision-guided munitions trace their conceptual lineage directly to the Nord. Inertial navigation systems evolved from gyroscopic stabilization, automated pods, descendage of the analog computer, and telescope integration, fire control integration. The concept of linking sensors directly to weapons. The Joint Direct Attack Munition JDAM represents the Norden's spiritual successor. GPS guidance and inertial navigation achieve 5-meter accuracy from 40,000 feet. That's the precision Norden promised in 1937. Finally delivered 60 years later. Why it matters today. The Norden teach us a critical lesson about military technique. Specs don't equal performance. On paper, the Norden could hit a 50-feet circle from 20,000 feet. In combat, it hit 1,000 feet circles. The difference wasn't the technology. It was the operational environment. Modern weapons face similar gaps. Precision-guided munitions achieve incredibly accuracy on test ranges in combat with electronic warfare, GPS jamming, and target identification challenges, actual performance degrades. Understanding this gap between laboratory performance and battlefield reality shapes how militaries develop and employ technology today. The uncomfortable truth. Post-war strategic bombing surveys revealed an uncomfortable fact. Allied bombing killed approximately 600,000 German civilians. Another 800,000 were seriously wounded. The Norden bombsight was supposed to prevent this. Precision bombing meant hitting factories, no thumbs. That was the promise. The reality. According to the U.S. Strategic Bombing Survey, fewer than 20% of bombs dropped on Germany hit designated military or industrial targets. The other 80% hit something else. Civilian areas, farms, empty fields, residentially. The Norden didn't make bombing precise. It made bombing seem precise. There's a difference. Let's return one final time to SCHWEIN Fort. Black. Thursday, October 14th, 1943. 6 OB. 7 shot down. Each aircraft costs $238,000. About $3.5 million today. That's $210 million in aircraft losses. In a plus $650 casualties among a replaceable trained aircrew. And the target, back to full production in 6 weeks. Was the Norden bombsight a failure? Here's the paradox. It failed to deliver its promised precision. But it succeeded at something perhaps more important. It changed how America thought about air power. Before the Norden, bombing was random destruction. After the Norden, precision became fatal. Even when we couldn't achieve it, we kept trying. That pursuit of precision led to smart bombs, cruise missiles, and GPS-guided munitions. Today's weapons actually can hit pickle-barrels from 4 miles up. The promise Norden made in 1937 is reality in 2024. But here's the final statistic that puts everything in perspective. In 1943, the 8th Air Force dropped 44,000 tons of bombs on Germany using Norden bombs. Today, a single B-2 Spirit stealth bomber carries 40,000 pounds of precision-guided munitions, 20 tons, and achieves better accuracy than an entire 1943 bombing. Wing, 1 aircraft, flown by 12 people, accomplishing what required 300 B-7 South and 30,000 aircrew. That transformation started with Carl Norden's obsessive belief that machines could calculate faster and better. 10 humans, he was right about that part. Haggis built his machine 50 years too early. The technology couldn't match the ambition, but the ambition shaped everything that came after. If you found this story fascinating, hit that subscribe button. Next week, we're covering the proximity fuse. The radar-guided artillery shell that changed naval warfare overnight, and actually live it up to its promises. Drop a comment. What World War I technology should we cover next? Let me know below. Remember, the history of warfare is the history of promises made to be engineers and kept by soldiers. Sometimes the engineers get it right, sometimes they don't, but soldiers always pay the price. Thanks for watching.